All right. For the Related Rates Party finale, the fireworks are shot up at a rate of 150 feet per second from a platform that is 70 feet away. Due to the wind, the fireworks take a path of 30 degrees from vertical, so instead of going straight up, they went 30 degrees off centered toward us. When the fireworks have traveled a distance of 40 feet, so they've shot up 40 feet, are they moving toward or away from our faces? And at what rate? So they're this far away from our faces, but they're not standing still. So this distance is either getting bigger or smaller, toward or away from our faces. Lovely. I think a nice place to start with is if we're looking for the rate of change of this side of this triangle, could we figure out how long that triangle side is? Do you know how to do that? You can't do the Pythagorean theorem because it's not a right triangle. Did you say the law of cosines? Great. We do have sort of a side angle side situation here. Maybe we'll call this side A and this side B and this side C. And so here we go, law of cosines. C squared equals A squared plus B squared minus 2AB cosine of theta. I guess we're calling this theta. And really in calculus, you always want to make sure you do that in radians. It's just a rule, you know? So C squared equals, plugging in all the things I know so I can find that other side of the triangle. Pi over 3. Cosine of pi over 3 is just 1/2, so that shouldn't be too bad. It comes out to 3,700, so C is the square root of 3,700, and I'm going to leave it like that. Cool. So now I know all the lengths and stuff. And actually, I think now might be a good time. I like to always make a little chart. I don't know why. It helps me think. So I'm going to write down my A, my B, my C, and my theta in radians. And then I can list my rates of change too for each variable. Then I know I'm not missing anything. All right. So the only rate that we had was at 150 feet per second, and that was the rate at which side A was changing, right? So side A is 150. You gotta think, is that positive 150 or negative 150? And the trick to that is this side of the triangle getting longer or shorter? In this case, it's getting longer because that's still propelling upwards, so positive 150. Let's see. Oh, you know our d theta dt would also have to be in radians per second, because like I said, calculus always in radians. How fast is this angle changing? You know, that angle doesn't change, does it? Like, that path is sort of determined to be 60, so just 60 degrees, and it's not the derivative is 0 then. That's staying a constant pi over 3 angle. Is there anything else that's not changing? I think B is not changing, right? We're not running toward the platform or running away from it. So dB dt would also be 0. And is dc dt what they're wanting from us? The rate of change from our faces. Yeah, the rate of side C. Perfect. And then, I don't know if you've noticed this yet. This is our 4th example. Have you noticed that whatever equation we use to figure out like the quantities we need, we wind up using that equation again to build our derivative function? So we use this law of cosines to find side C. So we're going to use the law of cosines as our function to differentiate. I don't know if you're having nightmares already too, but check this out. We've got, the 2 is just a constant, but we've got an A, we've got a B, and a theta. that's going to require like a triple product rule almost, right? With the A, the B, and the theta. And I don't like that. And one thing that we didn't mention before, because we didn't really need to, but did you know that if a quantity is not changing, then that quantity is not a function of time, and its derivative. And what I'm trying to say is that we can actually plug in before the derivative quantities that aren't going to change. So I'm plugging in that 70 for side B. My angle's not changing, so I can plug in the pi over 3, because those aren't functions of time, they're constants. And so I can plug that all in before I take the derivative. Normally you don't want to plug anything in, but because those are constant, you can plug in before. I'm just going to simplify this. Always better to simplify before you try to take a derivative. Cosine of pi over 3 is half, so 2 times half is 1, and I have a minus 70a. All right, I think it's time for a derivative. The derivative of c squared is 2c times c prime, dc dt, because c is changing as time changes. The derivative of a squared with respect to time is 2a times dA dt. The derivative of 4900 is 0, and the derivative of minus 70a is minus 70 times a prime. Sweet. Now we can plug in the things that we know. I know C. I wish I knew dc dt. Positive 150 plus 0 minus 70 times positive 150. So dc dt, all this junk comes out to 1500, so I'll just divide over my 2 root 3700. dc dt is about, are you ready for it? Comes out positive 12.330. All right, the math part is done. Now we have to think, what does that stand for? So I know it's talking about this side of the triangle, yeah? It's the C side of the triangle. It's positive. Our derivative is positive 12.330, which means the rate of change of this side is positive. That means it's getting longer, which means that I suppose the fireworks are kind of past the point, so that now they're getting further away from us, and this side is getting longer and longer. That's why that came out positive. And so if I were going to write this in a complete sentence, I would say that the fireworks are moving away from our faces at a rate of 12.330 feet per second. I love related rates.